Hello, ladies and gentlemen. We're going to be doing a little bit of notes here on friction. And a lot of this is going to be based off of some of the things that in person we saw doing the shoe lab, where we're dragging the shoes across surfaces and we're measuring how the force changed. And in that situation, most people saw that, let's see if I can draw a little shoe here real quick. Swoosh. As we were exerting a force to pull the shoe across the surface, we were trying to pull it at a constant velocity so that acceleration would equal to 0. So if we had some pull force Fp acting on the shoe, sorry, my handwriting's a little messed up there, and we're maintaining a constant velocity, that means there had to be some sort of other force acting externally to the shoe, in this case friction force, that was keeping it in equilibrium. So we were able to say that the pull force seemed to be related to how much weight the shoe had, which is also going to be related to what's called the normal force. So the weight force acting on the shoe going down, Fg, sorry, there's a terrible little diagram up at the top here, but the weight force that we had acting on the shoe as we increased it, the pull force required also increased. And we ended up seeing a relationship that, well, if everything went according to plan, if we had the weight force versus the pull force, we saw something that was pretty linear. And we were able to even take that linear relationship and predict what a pull force should be within, a reasonable uncertainty level if we kept increasing the weight. So some people did see some interesting things, like the shoe got really, really grippy if we put too much weight on it. And that gets into deformation of the shoe and changing how much friction there is. But in general, we saw this sort of relationship. What we're going to see in the future, though, is the weight of the object is not necessarily the best indicator once we start going on inclines. What really matters is the normal force. How much force is the surface having to support with? That's going to dictate how much friction force we experience. And our analog for pull force to friction force still holds. So this linear relationship we see in the graph could be pull force is equal to some constant times the weight of the object, but instead we're going to flip that around and say that our pull force is really equivalent to friction, and the weight force in this case on a level surface was equal to the normal force experienced by the object. The question then becomes, what's this K? What's this constant of proportionality? Well, since we're measuring how much friction we get, this constant becomes called the coefficient of friction. And we give it the Greek letter mu, or mu. I'll flip-flop back and forth between saying those two different versions of the incorrect pronunciation of that Greek letter, but that's how we refer to it here in physics. So the force of friction is going to be F sub F. It's measured in newtons. The normal force is a force measured in newtons. So that means the coefficient of friction is unitless, has no units. It is just a multiplier. It's kind of like a decimal version of a percentage. So if you have a very, very, very small coefficient of friction, that means no matter how big the normal force, no matter how big the support force from the surface, you have very little friction. And so if this were, say, 0.01, that means the frictional force experienced would be 1% of the normal force the object is supported by. If it was a mu value of 1, that means 100%. So if something on a flat surface weighed 1,000 newtons, in order to slide it, you'd be facing 1,000 newtons of friction. So that's one way to think of it. The larger the number for mu, the more friction you're going to experience. Now, there are two flavors of friction, as I often like to say. There's the I'm stuck and I can't move, which we call static friction, and we give that the subscript S on the letter mu. It's generally speaking, well, it's always larger than the kinetic friction coefficient we'll look at in a second, but it tends to be fairly big. When two objects are resting on top of each other, there's no motion between them. There's some stuff going on molecularly on the subatomic level as well, nuclear forces and whatnot, electrostatic forces. all that are trying to prevent these things from moving away from each other. They don't want particles to get closer or further away. So there tends to be some resistance to the sliding. So we would say that this is a large value, but what's interesting is static friction is actually adaptable to the applied push or pull up to a point where we have a force applied that is mu s times the normal force. So the amount of friction we have for static friction, which make life just super fun for you here, I'm going to write this as F sub Fs. We're doing double subscripts here. It's actually going to be less than or equal to the coefficient of friction times the normal force. Now, we saw this, and I apologize, let me get this calculator out of the way. We saw this when we were playing around with force sensors. If you collected data as time goes by for the amount of pull force, you often saw, especially when you loaded up the shoe with a lot of stuff for the block of wood, whatever you're using, when you loaded it up, the force started going up and then it kind of went down. There we go, the line just showed up. There's a increase in force, increase in force, increase in force, and then the shoe starts to move. This zone to the left of the peak, that's static friction. It wasn't in motion yet. The shoe, the block, whatever you're using in the lab, it was not in motion. It was still it was in static equilibrium. It wasn't moving and it wasn't accelerating. And you kept building, 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 and then all of a sudden, the shoe scooted. And once it went into motion, the force tended to drop off. Now, not all graphs look like that. Some people might be saying, Mr. Zook, my graph just looked like this. And in some cases, there's not that much friction, and so you pull hard enough that it goes into motion right away. But if you pull very, very gently, you get a force profile that looks like this. So this means that the amount of force you're pulling with was being counteracted by the static friction before it went into motion. As you pulled a little bit harder, friction increased until you got to this point right here. Oops, that was the eraser. Until you got to this point right, having all sorts of problems here with my my computer here. Till you get to this point right here, which is the maximum force of static friction. Once you hit that, it goes into motion. We're no longer in static friction, we're in kinetic friction. Kinetic friction is when you're in motion. And this mu value is smaller. It has to be smaller. You're not giving a chance for the particles to settle. And it's a constant. So once you're in motion, this should stay relatively constant as long as the surfaces don't alter. So instead of saying that the friction force, like in static, is less than or equal to that value, like it builds up to a point and then snaps, the kinetic friction is always going to be the same. We would say that F sub Fk is just equal to mu k times the normal force. Now on the AP exam sheet, they give you this version for static friction, and they just leave off the S's. They just say that friction is less than or equal to this relationship, and they expect you to kind of remember which is which. So I think that's about as much as we can say about friction without actually doing stuff in live class with friction stuff. So all that leaves us is trying to apply this and using some of the other dynamics equation stuff that we've used in the past. So we want to do a couple of examples. Let's say we got this grimacing person right here. They have a 4 kilogram box and it's being pushed horizontally. If it takes 15 newtons of push force, realize that says 14.5, let's fix that. If it takes 15 newtons of push force just to overcome static friction. We'll talk about like what that means, but you keep pushing, 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 nothing happens, and this peak right here is 15 newtons on your graph if you were to have a force sensor hooked up. What is the coefficient of static friction mu s? So we're going to start off with this by drawing a little, we'll draw some stuff on top of the picture, but we also want to draw a free body diagram. So I can scribble all over the place, but for the free body diagram, I'm going to have the force of gravity acting down, Fg, or you can write m times g. I'm going to have the normal force acting up. I'm going to have the push force, we call that Fp. Some people put Fa for applied force, but Fp for push works for me. And since we're assuming it's just enough, we're going to draw this as if the friction force is equal in size to the push force. Now, technically speaking, you're probably thinking, well, wait, if it's overcoming it, doesn't this have to be bigger? Well, let's assume that if this is 15 newtons, that this was 14.99999999999. You know what I mean? It's so infinitesimally smaller than the push force that if we go to normal sig fig sort of stuff, 1 or 2 digits, they're the same. So if we draw a free body diagram like this, we can now go ahead and do some equations. So I can say in the x direction, sigma fx, I'd have F push minus F friction should be equal to, in this case, again, we're saying that they're like equivalent to each other, 0 newtons. And I can say that in the y direction, I've got normal force up minus Fg down should also equal 0 because it's not moving up or down. And at this point, you might be thinking, oh, wait a second, normal force is important. That's why we were solving those questions and solving for F normal in class. And it wasn't just to make your life miserable and do a bunch of calculations. We actually need to know what the normal force is. So if we wanted to extend this problem and try to solve it from the x stuff, I can say that the push force must be equal to the friction force. But I'm going to go ahead and substitute in here mu s multiplied by normal force. I'm going to make that substitution because I got it up here. So I've got that as my push force. And if I were to, I realize I'm exposing the next example. If I were to also solve the other problem here, normal force should be equal to the weight, but let's go ahead and put that as m times g. Now, if my goal is to figure out what mu s is, I've got enough stuff. I know what the push force is. I know it's 15. The normal force is equal to m times g in this case. So I can go ahead and substitute in the normal force up above and calculate an answer. I can say that 15 newtons is equal to mu s multiplied by mass times gravity. The mass in this case was 4 kilograms. Acceleration due to gravity, 9.8. If I do the old calculation on that, now's where I'm going to go ahead and pull my calculator back on the screen. I would have 15 divided by 4 times 9.8. And I get 0.383, or let's just call it 0.38. Again, there's no units for the coefficient of friction. It's just a number. So this number essentially says that whatever the normal force is acting on this box, I've got to exert 38% of that force in order to get it, just to get it to budge. Now, of course, this is where I'm just pushing enough to just break static friction. If I were to push harder, I would then definitely not have 0 net force. I would have to say, well, I know that this was limiting at 15. If I push with more, I should have an m times a there, and I'd have to be able to figure out what the acceleration is, which is what we're going to be doing in the next problems. So at this point, it's about 15 minutes in to this video. You need to take a break. Otherwise, we're going to take a look at what if I modified the problem. What if I took the same surface, and in this case, I applied my push force at a downward angle, and I increased it. I pushed even harder. I'm just like, man, I want this thing to get moving. Somehow I got taller as well, so I'm able to do this. But let's say I push it at an angle of 30 degrees downward. What would be the situation? Would the block move? So in your head, you can start forming some ideas. Well, if I'm pushing down, that should increase the normal force because now I'm going to crush the object into the surface more. But I'm also pushing with more force sideways, so will that counteract? Will it work? We would expect that whatever happens, if the push force component going sideways, this FP, is greater than whatever the friction force is, then we should get some motion. If they're equal, then it would stay in equilibrium and not move. And if the push force was less, it's just going to sit there because the friction force would be static friction, it would just ramp up. So let's go ahead and do some free body diagram and some setup for this. I'll do the free body diagram down below. I would have the weight force going down. I'm just going to write this as m times g this time. And I'm also going to scroll down a bit because this is way too low on the screen there. I then would have the push force also going down like this. And because there's two things going down, I got the mg going down and I got the push force going down and to the right, I'm going to have a really big normal force. Normal force is going to go up, 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 up like that. And then the only other force acting on the object would be the friction force going towards the left. Remember, free body diagrams, no components, just the actual pushes and pulls. Now, of course, in order to do some calculations, I've got a force. It's at an angle to my coordinate system. So yeah, if the push force is going down to the right, I need to calculate how much is down and how much is to the right. And I'll use my sines and cosines for that. So let's set up some sigma fx. Force is going to the right. I'm going to have the FP's cosine components. Oops, that's weird. Don't put the theta there. Then to the left, I'm going to have friction force. And all that is going to be equal to question mark? I don't know. I could say that it's equal to m times a, and that the a is my question mark. Don't know. What's it going to be? Then I can write an equation for sigma fy. I'll have f normal going up minus the combination of mg and the FP sine 30. And since I know it's not sinking in the ground, I'm going to go ahead and say that's equal to 0. So at this point, this is a problem that you can work out. In this case, it's the same box on the same surface. So that means we know what mu s is. It's right there. We had it before. So if we go through and put little check marks over things that we know what the m is. It's the same box. We know what g is. We know what the push force is. Again, we know what the push force is. Friction, the equation for that we know is mu times normal force. And since down here we know everything but the normal force, we could calculate what the normal force is and pop it in there. And then we could figure out what's happening. So the big thing I want you to do here, pause the video, take a look at this, see if you can get to a conclusion. If FP cosine theta minus the force of friction is 0, box doesn't move. If this difference is less than 0, if it's a negative, box definitely not moving. Friction can't win. Right? The box doesn't slide backwards because you're not pushing hard enough. Give it a shot, and I'm going to reveal what the answer is in just a second. Okay, so got some solutions up here. If I take this normal force equation here, I can add that term over. mg plus this FP sine 30, put in the values for that, I get 54.2 newtons. Then if I take the x equation and I just kind of rewrite it with the friction equation, mu s times normal force, I can put in those values and let's see what I get here. Let's see, 30 cosine of 30 minus 0.38 times 54.2, and I get 5.38. So 5.38, that's greater than 0. That means that this block has more push force acting on it than it has friction force. even though you're crushing the object into the ground somewhat, you still have, even though it's increased friction, you're still pushing harder than the friction that you're going to get. So in this case, I have a net force on the object. I'm beating static friction. I'm in the kinetic zone. So I'm sure you might be able to guess what the next question is, the last example problem. Well, what's your acceleration then? So for example 3 here, if the coefficient of kinetic friction, once you break static friction, you're in kinetic zone. Once you break this static friction, you're in the kinetic zone, and the value of that between the box and the ground is 0.25. What would be the acceleration of the box? So we're going to not have to write a single new equation. We already have the equation right here. Bloop. We just have to modify this sigma fx and say, instead of static, let's say that it's kinetic friction. So if we rewrite the formula, we say this net force in the x direction is going to be Fp cosine 30. Now we've got values for it, but I'm going to write it as an expression first, minus now mu k times the normal force equals m times ax. We can solve for the ax. That's an unknown. We've got every other value, and we can plug in the numbers and solve. So I've got 30 newtons, cosine of 30 degrees, minus new coefficient of friction, oops, I wrote that wrong, 0.25, times the normal force is the same, it didn't change, it's still 54.2. And that's going to be equal to m times a, and our m was 4 kilograms. So from that, we can calculate what the a is. So let's do that on the calculator here. See, 30 cosine 30. By the way, remember to put yourself in degrees mode. Minus 0.25 times 54.2. Notice smaller coefficient of friction times this. I should get a smaller force of friction there. Let's see, I get that, and I get 12.5. So this is how much net force I had the instant that I was trying to push on it. But as soon as I break static friction, that's not my net force anymore. The net force bumps up. Now it's 12. And if I divide that by 4, I should get the acceleration rate of 3.11, or this is called 3.1. Now this is not a completely uncommon type of problem. It's not trivial though. There's a lot of steps to it. But something like this is a very good example of an AP style multi-step FRQ. They'd probably throw in something else as well. But it's systematic solving, drawing free body diagram, writing equations for the x and the y direction. A little bit of conceptual stuff in there though of deciding, well, how do I know if it's going to be moving or not? We'll be practicing more of this, but for now, that's all I got on this.